Hey everybody, and welcome back to Calc 3 Online. So in this video we're going to talk about a new coordinate system. So we just spent some time working with cylindrical coordinates, but there's another very famous one that usually pops up around this time called spherical coordinates. So just like with cylindrical coordinates, there's certain things, namely like spheres, that are much easier to work with given spherical coordinates. So to just kind of show you a little bit about what they are, and I'm going to actually go through all the conversions and all that stuff on the next slide, but spherical coordinates, instead of an x, y, z, there is this is pronounced, this little p thing is rho, and it's spelled that way, R-H-O, and then theta, and this is phi. And the rho is basically like your radius, so you still are measuring it from the origin, and you're still measuring out from the origin, just like R was measuring in the plane for like polar, and I guess cylindrical too. So that part's still pretty similar, but since it isn't in the plane necessarily, it can be anywhere in 3D space. We're calling it a new variable, but it's basically the radius. And then theta is normal old theta. So that is like the angle that starts on the x-axis here and goes this way around, and that's the polar theta. Phi is a new angle, and it's the angle. It's an angle you measure actually from positive z-axis, and it kind of goes down. So other weird thing is that theta goes a full 2 pi, right? So I guess it's good to put that back too. So theta goes from 0 to 2 pi, but phi doesn't need to go all the way around to 2 pi. Phi goes from 0 to pi, and it does include both of those. Actually, if you didn't include one of those, then you'd have like a dotted line here. So like you wouldn't be able to get like one of the North Pole, let's say, or the South Pole. And I can't show it here, but this is just a screenshot, but I will show this video, which I think helps to see how these angles work, and I'll say a little more about it in class. But you can kind of imagine that if you let this angle rotate down halfway around, right, but then this one rotate fully around, and let R just shoot out to infinity, right, you should be able to get all of 3D space still. And so that's the idea. And just to kind of give you, I think, a little bit, help you understand what these things are doing, I wanted to talk about these two equations. So phi equal to a constant, so is a very specific shape that actually you know of. If you think about it, so it's saying that theta can be anything. So you can just kind of go fully around the axis, the z-axis, right? Rho can be anything. You can go out, let the radius go out to infinity in any direction you want. But if you fix this angle that comes down, right? So I'll try and draw it here. So say we fix this angle, phi, to be, that's my c, okay? But then this right here can rotate around, right? You can kind of see that you would get like a cone, and that's really what it is. You basically just get a cone that's kind of infinite. It's like shooting out forever, so it's like an infinite cone, is really what it is. And if you can get like a skinnier cone, right, if this angle is smaller or whatever, larger if it's larger. But that's what that is. That's the equation of a cone in spherical coordinates. And then if you let theta equal a constant, so this time the phi angle is allowed to be literally anything. So you get kind of a vertical infinite distance. So that's how you're getting like up and down forever. And then rho is starting like here and shooting out forever, right? And so if you kind of mix those things together, you can kind of see that you would get basically, this one is like an infinite half plane, is really what that one is. So this goes on forever, up and down. It doesn't really end right there. It keeps going down. Just hard to kind of draw. And then it goes out forever too, because of the row part. So those are kind of two weird examples, but this one, phi equals c, cone, theta equals c, half plane. All right, so I wanted to do, I really want to build up where these even come from, like the conversions, I guess. So based off of just this figure alone. So from this figure, we're going to determine basically an expression for z, x, and y, or x, y, and z, in terms of rho and the two angles theta and phi. So I always thought the easiest one to start with is always this triangle up here. So it's a right triangle, okay, but notice the right angle is up here. So this is a hypotenuse for that triangle, all right? Given that, you can see that, like, if you do cosine of phi in that angle, right, it's going to be z over rho. Let me draw my rho a little better. This is how I draw rho. I actually start at the bottom of the p, and then I curve up, and then straight down, like that. So that means that then z would equal rho cos phi. And that is going to be one of my conversions that I would use. So I wanted x, y, and z in terms of rho and the angles. So this is z in terms of rho and one of the angles. And that is actually what we use to convert z for spherical. All right, so kind of similarly, I think I'm actually going to get rid of this. So if you look at this, I did a horrible job at line. That is really a rectangle, right? I mean, some of the right angles are already drawn. And so most importantly, the R here is the R here, okay? So if I do that, okay, I'm going to erase that part. So now if I use this triangle up here again, okay, I can take the sine of phi this time and see that the sine of phi would be equal to R over rho, okay? Or R would equal rho sine phi. I'm doing that because we know polar, we know x equals r cos theta, and we know y equals r sine theta, right? So if I had an expression for r, which I now do, I could go and pop that in to get expressions for x and y. So x equals r, but r can be understood as rho sine phi, and then cos theta. And then y equals r, but again, r can be understood as rho sine phi, and then sine theta. And that are the other two that you need, okay? So these two things, which I really just get out of doing triangle trig with this upper triangle, and I guess also recognizing that this r matches up here too, right? Because it's like a rectangle. That gives me a way to convert, things like this. So if I have x squared plus y squared plus z squared, which hopefully you should kind of recognize as the beginnings of a sphere, right? This ends up equaling a very nice thing in spherical coordinates. So x is this rho sine phi cos theta, and y is rho sine phi sine theta, and z is rho cos theta. Nope, messed it up. Rho cos phi. And I'm just going to plug all those in squared. So I get this. Okay, so this is my x, my y, my z. I do expect that you know these conversions too, just like I expect you know these. You do want to make sure, if you want to think of the picture and come up with them from the picture, but hopefully use them enough that you can remember. The way I remember them is honestly the way I drew them here. So this one, I can usually kind of just recreate the picture of quick. Then this one, I just think that I know that there's this common part in here, and I know that x is based off of r cos theta and y is r sine theta from polar. So if I can just remember that green part, I just know to pop that in for these two. Okay, so if you look at what we got, this thing can simplify, because what we have down here, you can take out, let's underline it here, so rho squared sine squared, right? You can take that out of the first two terms, and you get that, plus this, and then that's just my z part copied over. Oops, wrong angle, sorry. Okay, and then this is a 1, right? And so then I'm getting rho squared sine squared phi plus rho squared cos squared phi. And I'm going to take out rho squared this time. And then I get sine squared plus cosine squared again. And so use the trig identity again. And you get rho squared. Which really shouldn't be that surprising, because we know that like the equation of a sphere is like, this is a sphere center at the origin, which is what we're doing, would equal all this stuff, which equals the radius squared of the sphere. But the radius is rho, right? So it should have equaled rho squared. It shouldn't be surprising. So just to kind of show you something that hopefully has some context with you. But yeah, this is the kind of thing, like if you see this in an integral, like a triple integral, you might want to think spherical coordinates, because that big mess is going to always simplify to this. That's like the benefit of this stuff. All right. So I just want to do one of these kind of conversion problem sort of things. So we always, I always get the question, which angle is which? And there is a very specific order, okay? Maybe I'll do this in yellow. It's always going to be rho, the radius part, then the polar angle, then the 3D kind of angle, the one that comes down from the z-axis. It actually was written here too, and I probably should have stressed it, but always rho, theta, phi, okay? So that is a point in spherical coordinates, okay? So 2 out, and then spin, in the plane, pi over 4, and then drop down pi over 3, you'd be right there, okay? And I want to plot that point in rectangular coordinates, okay? So we know that z is rho cos phi, okay? So z is 2 cos pi over 3, which is equal to 1, all right? And that seems believable, that that'd be up at 1. Then we've got that x is rho, sine phi cos theta. So x is 2 sine pi over 3 cos pi over 4. And if you do all that out, you get the square root of 3/2, which sure seems reasonable for, I'm going to say it's right there, square root of 3/2 for that one. And then lastly, if you do y is rho sine phi sine theta, which in this case is going to be 2 sine pi over 3 cosine pi over 4. And if you do that one out, you also get the same thing. So if I kind of go right there, this point right here is square root of 3/2 again. So fairly believable, probably. You can go to like Math 3D or something like that. If you want to like really check it, you can kind of plot this and see that that really is how it works out. You could put in like the y equals x plane or something like that and see that it lines up perfectly here. And, because this lined up perfectly, it kind of makes sense that this x and this y should have been the same, because pi over 4 would be halfway in that like quadrant, right? So that's kind of how we go back and forth. And what we're really going to be doing with it is integrals, okay? And so we need to know dv in spherical coordinates, okay? And it really does come out of length times width times height, again, like all these things have kind of come from this. And we saw this, literally if it was a triple integral with rectangular coordinates, it would literally be, dx, dy, dz. Then we saw it with cylindrical coordinates. It was a little different, and it'll be a little different here, but it's really being built off of length times width times height, okay? There's just going to be a computation for this, there's going to be a computation for that, and then there's going to be a computation for this back here, okay? And those three, these are arcs, right? This is an arc, and this is an arc because they come out of the angle. And then this is like a line segment, I guess we'll say, okay? This one's probably the easiest one. If we call that the length, let's say, then that one's just truly d rho, right? There's going to be some sort of, change in the radial measurement. And so that change, that infinitesimally small little differential there, is d rho. That's like the nicest one. Okay, so that's that one done. The other ones you have to think about a little bit more. So to do these other ones, it really goes back to polar. Basically, it's an arc length problem again, where the way we compute arc length is radius times the angle, right, for the arc that it maps out. And so we're just going to use that. So let's do the red one next. So the red one's probably the next easiest one. This angle in here, right? That angle is d phi, okay? And the radius is rho, right? And so those two things, like if you just do, if you do rho times d phi, right, which is the angle, then you would get this arc length, which is another one of these two measurements. So I'm going to get rid of that, but I didn't want to get rid of all that. I want to get rid of that. So this red arc is going to be rho then d phi. All right, so we've got this one now done. Let's say we did length and width, and then for the last dimension of this kind of spherical cube-like unit cube thing, we need to get this green chunk right here. So that is a little bit tricky, I think. So you need to kind of see it, I think, because like the angle is not so bad. The angle is going to be d theta, right? Because there's like a change in theta down here. The radius is probably the trickier part, okay? And it's almost easier probably to look at it down here. So the radius for this one, if you project it down, right? Basically, you're looking at what's hard to do. So we're talking about this kind of part in here, and the radius that comes out to that arc is the radius from back here, right there, right? So it's literally r. It's that r, right? The polar r. So for this green one, the radius is what r equals, which is like true radius, which is rho sine phi. And then the angle is d theta, right? And so you come out rho sine phi, and then you span d theta, right? And that would be the arc length of that little part up there. So you kind of get the dv, the volume of this little kind of cubey, by doing this times this times this. And so the last one is rho sine phi d theta. And typically we put it all together and we say that dv, you multiply this row and this row, and so you get rho squared. And then you have a sine phi, okay? And then you have a, whoa, I messed up badly there. So d rho, a d phi, and a d theta. So in polar, right, we were getting an extra like r from in the dA, right? But here for dV, we get this rho squared sine phi part popping up, and then we have all three of my changes in the unit. So you have to remember that this little part is here. If you switch to spherical, you've got to deal with that. Okay. So a lot of setup, but I want to make sure we have time to go through one of these examples. So I want to use spherical coordinates to find the volume of the solid that lies above the cone. So this cone down here, x squared plus y squared, square root of that thing. And below the sphere, x squared plus y squared plus z squared equals z. Okay? And so it's we're finding the volume of that solid, and we're going to do it with a triple integral. All right? And so we know that we've done this before, where if we take the triple integral of 1 dV, that is equal to volume, like true volume. And that's basically what we're going to do. But here, when we do a triple integral, we have, and we're going to do it in spherical, we're going to have this weird rho squared sine phi that I just kind of showed in the last problem pop up. So we're going to have a d rho, d phi, d theta. Okay, and so let's talk about some of the angles, I guess. So theta, we're just going to start kind of outside in. We're doing a full 360, right? Full 2 pi. So we want theta to run 0 to 2 pi, to get all the way around that cone and sphere and all that. Phi, though, this angle that measures from here down, okay, is not, you don't want a full pi of it. So you only want to go down to this part of the cone, and that part of the cone that's smack dab in like the middle of here, and so it is pi over 4. So we're going to let phi run from 0 to pi over 4. So that's just that little angle right there. And then for rho, okay, we need to go from 0 definitely, and we have to so we'll put that in, I guess, right there. And then we have to think about this a little bit. So we want to think about where. So what was I saying? So we want to think about the fact that we're going from 0 in rho, right, out to this surface out here, this sphere. But we need to figure out what this is in spherical coordinates, right? So we talked about how this part on the left, all of this, would become rho squared, right? We also said that z, if you go back like here, right, z is rho cos phi. So I can set this equal to rho cos phi. And then I could divide out by phi, really, because it's non-zero. We're interested about the part that's non-zero, I guess I should say. So if we divide out by rho, we get rho equals cos phi. And so as an outer bound, right, it looks like rho is getting out to cos phi. So that's how I could actually get the upper bound for my phi, okay? So that's basically always, I think, the trickiest part. And then working through the integral is not horrible here. You basically, once you do the first one, you're going to do d rho. You're going to get rho cubed over 3, right? Or you can pull a third out. So we would have this. And I also plugged in cos phi. Okay, so I plugged in cos phi, to rho. And then I took the third out here. This is a nice u sub 1. You can let u equal cos phi, right? Then du is, well, even more importantly, minus du is sine phi, which, I've got the derivative in here. So if I do that out with that u sub, I basically, and then kind of resub, I'll get 1/3 0 to 2 pi, then I'll have a minus cosine of to the fourth, phi over 4, running from 0 to pi over 4, d theta, okay? So that's my phi integral. And then you do all that out. It's not horrible. You could take the fourth out, a negative fourth if you want. And, the integral of... Wait a second. Sorry. I don't need to worry about any of... This is actually much easier than I thought. I was about to say there was like a parts problem all of a sudden I saw in there. Anyways, okay. This is just going to be evaluated, right, at pi over 4. And so we get like 1/3 0 to 2 pi. And then if you evaluate that at pi over 4 and 0, right, you would get minus a fourth. Root 2 over 2 is cosine of pi over 4, all that to the fourth, and then you go minus a negative fourth, so plus a fourth times cosine of 0 is 1, so really just 1 to the fourth is 1, and then d theta, and since that's all constant, right, we could just multiply, when we do the integral of the theta part, we just multiply by 2 pi, really, so then we get like 2 pi over 3 times that big mess in there. So I'm going to be really lazy, and I'm going to call that squiggle. And then I would just do it all out in your calculator. No sense worrying about it. And my calculator told me pi over 8. So it's... that's really, it ends up being basically just a U sub is like the trickiest part, and then it's pretty straightforward. We're just messy kind of looking thing after that. But I do think this is kind of funny because it's how I feel about a lot of spherical integral problems. The setup can be kind of tricky and kind of weird, but then once you set it up with spherical, a lot of times these things, like if there's something with a sphere involved, they end up simplifying way down, and it's such an easier problem than trying to maybe do this with geometry or something like that. So sometimes actually when people ask me to do geometry problems, the way I think about them is with triple integrals, because that's how I can think of like volume, but I'll do it with like a spherical coordinate problem instead, because it'll help me do stuff like that. All right, so that is a good example of like how we can use spherical to definitely, here we're finding volume, like true volume, not like hypervolume or something, but I do want to kind of show a weirder one. So this is just kind of an interesting problem, and I'm not going to have time to do it all out, but I didn't really want to do it out. I just want to like talk through the setup of this problem. So anytime I see these things in a problem, x squared plus y squared plus z squared, my brain goes to spherical coordinates because it's going to make things easier. So this part, is equal to rho squared, and then square root of rho squared would be rho, okay? And then up here, right, that is equal to rho squared, for the same reasons, right? So we have e to the minus rho squared there. And then there's always going to be popping up this rho squared sine phi when you do these problems. And so we can do the same exact problem if, we can do like d rho, d phi, d theta. And so theta, this is basically full three-dimensional space right here, because we're going negative infinity to infinity on every x, y, z axis. And so rho would have to run 0 to infinity. Phi would have to be the full 0 to pi. And theta would be the full 0 to 2 pi. And so that would be an equivalent problem for this one. And it's a good one to try out and do. You should get 2 pi. You basically have to do like a U sub inside a parts problem, and then like another, like call it like a W sub eventually. But there's a lot going on, but it's a cool integral, and I'm happy to go through it in class if you ever want. But that is the setup, and see if you can get from there to 2 pi.